Hi, I'm Swapno, and this is the second session of Feynman's path integral that I'm teaching from this book that I wrote in 2023. So you'll find the link to this book with the video. Last time we discussed Gaussian integrals. Okay, so I will continue with the exercises that I assigned last time. Okay, on Gaussian integrals, and we will discuss more mathematics today. Okay, the prerequisites for the mathematics which are prerequisite for doing Feynman's path integral. All right. Okay, so let's get started. Let me just give a brief recap of what we did. So the main formula that we derived was this, okay? Minus infinity to plus infinity, e to the power minus ax squared plus bx dx is equal to square root of pi over a e to the power b squared over 4a. Okay? So that is the main formula that we derived. And we are going to do a problem, and I assigned two problems, okay, which are based on this formula. Okay, so let's work on the first problem that I had assigned. Okay. So the problems are in the additional exercises, of the book. So it goes like this: minus infinity to plus infinity. This is problem number 1. Okay. Dx e to the power minus k1 x minus a squared minus k2 x minus a squared x minus b squared is equal to an expression which is square root of pi k1 plus k2 e to the power minus k1 k2 divided by k1 plus k2 times a minus b squared. Okay, so this is the result. This is going to be very useful for doing path integrals. Okay, and see, these are like two Gaussians centered at two different values, and if you integrate this Gaussian, okay, with respect to x, you get an expression which is this. And see, in the exponent, you have the difference of the two centers, so the square of the difference of the two centers. Okay, and this property is going to be very useful. Okay. Okay. Anyway, so those are for later discussions. But first, how you derive this using this formula. Okay. By the way, you find all the solutions in Appendix 7 of this book. All right. So let's expand this. Okay, expand what we have in the argument of the exponential function. So you have minus k1 x minus a squared minus k2. Okay, I don't need the third bracket, right? So minus k2 times x minus b squared. So you can write this as minus k1 times, I'm expanding this, so you have x squared minus 2xa plus a squared, and then minus k2 times x squared minus 2xb plus b squared, right? And then you can combine the like terms, right? You can write this, it's just algebra, 7th grade algebra, all right? So x squared, and then you have minus k1 minus k2, right? And similarly, you can combine all the other like terms. So let me write down the final expression. That would be, okay, let's actually write it down in terms of a, b, and c, okay? So this is equal to ax squared minus ax squared plus bx plus c, okay? Where a is, you can check that this is correct. I'm just copying it from the book. It's k1 plus k2, that's a. And then b is 2 ak1 plus bk2. And then c is equal to minus a squared k1 plus b squared k2. Okay, so just, we expanded these two squares using a plus b whole squared formula, and we just combine the like term, we get this. Okay, very straightforward. All right. So now we're going to use this expression, okay, instead of this. Okay, and the ultimate goal is to use the formula that we derived, the last time. All right. So let's erase everything other than possibly these two lines. Okay. Right, so we're going to evaluate, we're going to use these constants to evaluate an integral like this. Okay, remember we started from a kind of a complex looking integral, so that really reduces to this expression. Okay, now c is a constant, okay, which you can take outside the integral. So you have e to the power c, okay, and then inside the integral you have e to the minus ax squared plus bx dx. Okay, now this is just same as that, right? So what you have is you have e to the power c and then times square of pi over a e to the power b squared over 4a. Okay, that's the formula. All right, and a, b, and c are, a, b, and c as appears here are given by these expressions. All right. Okay. All right. So basically the result is just this. This is your final result. So now all you have to do is to simplify this. So you can write this as square root of pi over a, and then you can just write the indices as the sum of two indices, right? Okay. And now if you use this expression for c and these expressions for b and a, okay, for a you're using that, okay? So you get this final expression, let me write it down here, which is square root of pi divided by k1 plus k2, and then e to the power minus k1, k2 divided by k1 plus k2, okay, times a minus b squared, right? Which is what we had set out to prove. Okay. Now, in order to get that, so you can immediately see this factor, is this, right? If you use this expression for a, you get that, okay? But you have to really do some algebra to, just sum these two expressions using these, expressions for a, b, and c. And if you have done the algebra right, then you should get this, okay? Okay, I'm not showing the algebra because it's really using a plus b whole squared and combining the like terms and so on, in 7th or 8th grade stuff, okay? All right. Okay, so this is the first part of the problem. This is the problem 1 that I had assigned. Now there's a note, okay, next to, at the end of problem 1, which says what happens when k1 and k2 are imaginary numbers, okay? Because in Feynman's path integral, you don't have real numbers for a and b, you have imaginary numbers, all right, as you will see later, okay? So, but you can use this formula, you can simply replace, k1 and k2 by imaginary numbers, and, you get the right expression, all right? But I realized after assigning the problem that, we haven't covered the complex numbers in the last class, so I'm actually going to cover complex numbers in today's session. So, let's wait to talk about the note, okay? All right. After I cover the complex numbers today, I'm going to get back to that issue. Okay. So and there's a second problem. So the second problem needs you to use the complex version of this. So I'll also do the second problem after having finished discussions on complex numbers. Okay, in today's session. All right. Okay. So let's start. Today's session properly. Okay. Because this was what we discussed so far is an assignment from the previous session. So today I'm going to start with series expansion. We will start with a very simple expansion, okay, which is called the binomial expansion, okay, 1 plus x squared, whole squared, which is 1 plus 2x plus x squared, right? Just a plus b whole squared formula. What happens when you do 1 plus x cubed? It's like you multiply 1 plus x 3 times, right? And if you have done your algebra right, you get 1 plus 3x squared plus 3x plus x cubed. Or I should have written it the other way. Let me see in which order I have written it. Okay, so it's 3x plus 3x squared. All right. Now it turns out there is a general formula for these types of expansion, which is 1 plus x to the power n is 1 plus nx plus n times n minus 1 divided by factorial 2x squared plus n times n minus 1 times n minus 2 divided by factorial 3x cubed, and so on, okay? So these notations are factorial, like, you know, factorial 2 is 2, 2 times 1, factorial 3 is 1 times 2 times 3, which is 6, and so on, okay? Okay, let's, I didn't prove this formula, okay, but let's check if this is true for, you know, either of these two. So let's start with this one, 1 plus x cubed, okay? So that means n is equal to 3, all right? Or maybe let's start with, you know, 1 plus x whole squared, which is actually easier, right? So let's take n equal to 2. Now notice one thing, when n is equal to 2, then this term is 0, okay? And so is all other terms, you know, after that, okay? Because, you know, you have this factor n minus 2 in all the terms, okay? So you have 1 plus x squared on the left, and on the right side you have 1 plus 2x, and this is n is equal to 2. So you have 2 times 2 minus 1 divided by factorial 2x squared, okay? And this is 0, so everything is 0 after that, okay? So what you have is 1 plus 2x, and this is just x squared, okay? 2 and factorial 2 just cancels out. Factorial 2 is just 2, okay? So what you get is this formula, right? On the right side, okay? Similarly, you can prove with n equal to 3 that this holds, all right? So when n is an integer, you'll find that this series kind of terminates, okay, after a, you know, after a few terms, all right? For example, for n equal to 2, it terminated here, right, at this term, all right? For n equal to 3, it will stop here, the series, okay, and so on, all right? Okay, now the beautiful thing about this formula is that it's true for all n. Like, you know, it's true when n is integer, it's true when n is a negative number, okay? Let me show you what I mean by n being an integer or a negative number, okay? Let's say that n is equal to half, okay? So when n is equal to half, then you have 1 plus x to the power half on the left side, and on the right side you have 1 plus half x, and then this is half times half minus 1 divided by factorial 2, and then you have half times half minus 1 half minus 2 divided by factorial 3x cubed, and so on, okay? So if you simplify, you know, you have to simplify these coefficients, and you will get an expression which is 1 plus half x, and then minus 1/8 x squared plus 1/16 x cubed, and so on, okay? It kind of continues, okay? The series doesn't stop. So the difference, you know, between n being an integer and, you know, n being a fraction is that for a fraction the series doesn't terminate. It is an infinite series, okay? You have an infinite number of terms, okay? And you can actually check that this is true by, you know, trying to evaluate, I don't know, maybe 1.1 to the power half, okay? So suppose you're trying to calculate that, so you can write this 1.1 to the half as 1 plus 0.1 to the power half, right? So you have 1 here, okay, and x is 0.1, so you can plug in x equal to 0.1 in all these terms, okay? And you'll see that, you know, if you keep, let's say, up to the 3 terms, okay, you'll get a number which is very close to the actual value of 1.1 to the half, okay? And the more terms you add, the better will be the approximation. You can actually just play with this, you know, with the series a little bit, okay? You can choose, you know, various different expansions, all right? And you can choose various different values for x, like 0.1, 0.3, and so on, okay? All right, and see that this series is actually valid, okay? It works, right? And n is not just, you know, it's not that n can be only a fraction other than an integer, but n can also be a negative number, okay? Let's try a negative number for n, all right? So this is our formula. This is our expression, and we will replace n equal to -1, okay? So what happens when n is -1? So on the left side you have 1 plus x to the power -1, right? And on the right side you'll have 1 minus x, right? N is equal to -1, and then plus n is -1, so -1 minus 1 minus 1 divided by factorial 2, and then you have x squared, and then plus you have -1, this is -1 minus 1, okay? This is -1 minus 2, factorial 3 x cubed plus da da da, okay? So you have 1 minus x, And this is 2, minus 2, right? And you have two minus signs, right? So it's plus, so you have plus 2. So the second term, it's x squared. 2 divided by 2 is x squared. Factorial 2 is just 2, okay? And what about this term, okay? So you have 3 minus, there should be a negative sign, and then you have, this is 3, 2, 1. So in the numerator you have factorial 3, and so do you have in the denominator, okay? So they cancel out and you have this, okay? So you have 1 minus x plus x squared minus x cubed and so on, okay? Now the thing is, you have seen this expression before, I think in 9th or 10th grade, when you are doing the GP series, okay, the geometrical progression, right? So in geometrical progression, you have what? You have a plus a times r plus a r squared plus, okay? And it can continue to infinity, right? When it continues to infinity, then this sum is written as a divided by 1 minus r. R is called the common ratio, right? So here you can see r is negative x. So your a, the first term, is 1, and then this term is a times negative x, okay? This term is a times negative x squared, and so on, right? So you have ar squared, just like that expression, right? So, you can, this is the, result for an infinite GP series. So if you use that expression here, what should you get? A is 1, right? And you have 1 minus, okay, r is negative x, so you have 1 divided by 1 plus x, okay, which is precisely what you have on the left side, right? Okay, so this formula, okay, you have seen this, so this formula is valid, okay, this formula is valid, okay, from the perspective of an infinite, okay, GP series or geometrical progression series, all right? So this formula holds for, integer n, integer values of n, fractional values of n, and negative values of n, all right? But one thing I'd like to mention is that, your x, there is a range of values for which, range of values of x for which this expansion is valid, okay? When, n is a fraction or a negative number. For example, the absolute value of x has to be less than 1, okay, for the series to converge when n is a fraction or a negative number, all right? Okay. So this is something you have to keep in mind. It's not true for all x, okay, for all n, all right? Okay, so now we are going to make a very interesting observation, okay? So we will still work with this formula, okay? Okay, so we trust the following formula now, right? We believe that it is true that 1 plus x to the power n is equal to 1 plus nx plus n times n minus 1 factorial 2x squared plus n times n minus 1 n minus 2 factorial 3 x cubed and so on, okay? All right. Now I'm going to make the interesting observation, okay, which is as follows. So let's say f of x is 1 plus x to the power n, all right? Now I'm taking the derivative, okay, of f with respect to x. So you have n times 1, right? And if I evaluate it at x equal to 0, what do I get? X is 0, so it's n, all right? And let me do d2f dx squared, okay? So I have to take the derivative of this, and I will have n minus 2, right? And if I evaluate it at x equals 0, what do I get? N times n minus 1, okay? Because this is just 0. And if you do d3 dx squared at x equal to 0, you will get n times n minus 1 times n minus 2. Okay, you can check that by yourself, okay? So, see, these are precisely what you have in the numerators, right? Okay? So you can write what you have on the right side. Okay, I'm going to write it here. So this is your f of x, okay? What you have on the right side is f of 0, okay? When x is 0, then f is 1. So 1 is f of 0, okay? And then nx is, instead of n, I'm going to write this, df dx at x equal to 0 times x, okay? Plus 1 over factorial 2 d2f dx squared at x equal to 0 times x squared plus 1 over factorial 3 d3f dx cubed at x equal to 0 x cubed and so on. Okay. This is called the Taylor expansion of a function f of x around the value x equal to 0. All right? So let me write this down clearly. Okay, I'm going to erase everything. Okay? So what I'm saying is basically that this expansion is not just true, okay, for 1 plus x to the power n, but it's true for any functions, okay? And I'm going to show you how that plays out for the exponential function, okay? So we have a hunch to suspect that the following formula, following expansion is true. F of x is f of 0 plus df dx at x equal to 0 times x plus 1 over factorial 2 d2f dx squared at x equal to 0 x squared, and so on. Okay? And let's just try it out, okay, on a function that we are quite familiar with. Okay, so let's take f of x equal to e to the power x, okay, the exponential function of x, all right? Then f of 0, okay, is just 1. Now, the exponential function has this nice property that all the derivatives are the same as the function, right? So df dx is e to the x, d2f dx squared is also e to the x, and so on, right? Okay, so f of 0 is 1, and so are all other, derivatives, like df dx at x equal to 0 is going to be e to the 0, 1, okay, and d2f dx squared at x equal to 0 is also going to be 1, and so on, right? So if I use this expansion for e to the power x, what do I get? 1 for f of 0, right? And then also 1 times x plus 1 over factorial 2. This thing is there. 1 over factorial 2 is there, right? It's just this part that's 1. Okay? So 1 plus x squared and so on. So 1 plus x plus 1 over factorial 2, x squared plus 1 over factorial 3, x cubed, and so on. So this is a familiar expansion of the exponential function. Right? An exponential function can be written as 1 plus x, and so on. Okay, it's a very nice expression for the exponential function. Okay, so you can check that this is correct by once again, taking a specific example. So it's the example 5 in the book. So you're asked to evaluate e to the power 2.1. Okay, approximately evaluate it. Okay, so this is an interesting point. Okay, so these series expansions can be used to approximate a function, right? So if you trunk it, up beyond a certain term, all right, then there's an error, okay? But sometimes you need those approximations. They're very useful, okay? For example, if I just keep the first two terms, okay, I get 1 plus x for e to the x. If I keep the second, the quadratic term also, then I get 1 plus x plus 1 over square root of 2 times x squared, okay? So these approximate expressions are very important in physics, okay? In physics and engineering, okay? All right, so here I'm going to show an example of using the series expansion to evaluate e to the power 2.1, okay? So let's say, okay, but before that, let me just generalize the formula, okay? Because what I showed is, I showed the expansion of f about x equal to 0, but it turns out there is nothing special about x equal to 0. Okay, you can expand it about x equal to a as well. Okay, so if you do that, all right, then you get the following expression for Taylor expansion, and that is the most general form of Taylor expansion. So you write f of x, okay, is equal to f of a, okay, plus df dx at x equal to a times x minus a plus 1 over factorial 2, okay, d2f dx squared at x equal to a times x minus a squared plus dot dot dot, okay? So this is the most general form of the Taylor expansion, okay? There is nothing special about x equal to 0, okay? And I just realized, while giving you that example, that we have to use this expression, okay? Because we are trying to find, e to the power 2.1, right? So we will expand this about 2. So our a is equal to 2, all right? So that x minus a is just 0.1, okay? Obviously, x is 2.1, okay? All right? And I'm using that for the function. What is our function? F of x is e to the power x, okay? So if you use this function in this expression, you get e to the x implies that is equal to e to the power a plus, df dx is, df dx of e to the x is just e to the x, right? So this is a, and then you have x minus a, and then 1 over factorial 2, this is also e to the a times x minus a squared, and so on. Right? Okay, so now, a is 2, so you know all these values, right? A and, x minus a, right? So you can keep 3 terms, the first 3 terms, let's say, okay? Choose a equal to 2, all right? And x minus a equal to 0.1 and evaluate the right side, okay? What you'll get is very close to the actual value of e to the 2.1, all right? So for example, in this problem, I think I got, by keeping the first 2 terms, let me just write it down here. Okay, I got e to the 2.1 is approximately equal to 8.165, okay? Which is kind of close to, 8.166. I mean, if you just, if you just plug in 2.1, as the argument of e in your calculator, you'll get 8.166 and it continues. But up to the 3 digits, after the decimal, you see that the approximation gives a pretty, close value as the original, okay? Right? Okay, so this is the Taylor expansion. All right, this is something you need to remember. All right? Okay. All right, so today I'm going to, this is the last topic of today's session. Okay, it's complex numbers. I'm not going to finish the entire discussion, entire section on complex numbers. Okay, but I'll introduce complex numbers. I'll do a problem and get back to the the exercise that I had assigned in the last session. Okay, which involves complex numbers. All right. So what is a complex number? In order to understand complex numbers, you have to know about imaginary numbers, okay? So for example, I, okay, is square root of -1, okay? So this is called an imaginary number, okay, which is written as square root of -1. So now if you have 2 plus 3i, okay, which has the real part and the imaginary part, that is called a complex number, okay? And so if this is equal to a plus bi, then you can equate the real part to the real part and the imaginary part to the imaginary part. So you'll have a equal to 2 and b equal to 3. Okay? All right, so this is how the equality of complex number works, right? For real numbers, if you have x equal to 2, it means x is 2, right? For complex numbers, you have to equate real to real and imaginary to imaginary, all right? So let's use this just simple technique to do a problem, all right? So we will evaluate square root of I. Okay, what is square root of I? Okay, so we write this as a plus bi. Okay, and we'll square both sides. Right. So if you square square root of I, what do you get? You get I. Okay, and if you square that, I'm going to just use a plus b whole squared formula, or if that bothers you, because we're dealing with I and so on. So let's just multiply a plus bi with a plus bi, right? So you have a times a is a squared, right? And then a times b is a bi, and then this is b times a, right? So I'm distributing a to the 2 terms, and I got these 2, and then I'm distributing bi to these 2 terms, right? So I have abi plus bi times bi. Okay? So I have a squared. Oops, I think I missed something. Okay, so it's the first thing is a times a, okay, which is a squared, and then a times bi is abi, and then you have this times that. So b times a is ab, so you have another abi, and then bi times bi, right? Okay, so you have a squared, and these 2 are like terms, so you have 2bi, and that gives you what? Minus b squared, okay? All right, do you see that? Yeah. So you can write this as, these 2 are, okay, by the way, a and b are real numbers, okay? That's the assumption. So you can combine these 2, a square minus b square, and leave the imaginary part separately, okay? And then equate real part to the real part. So what is the real part to the left side? It's 0, because there is no real part, right? So that means a square, I'm going to write it here, okay? That means a square minus b square equal to 0. And you have this equal to that, which means 2ab is equal to 1, right? Now you see that, this is just, you have two variables and two equations, right? So you should be able to solve for a and b. Okay, let's do that, right? So from the first equation, you get a squared equal to b squared, right? So that means a equal to plus minus b. Okay, so let's start with the negative value. Okay, let's say a is equal to negative b, and then I'm going to substitute this expression into the second one, which is 2ab equal to 1. If I do that, then I get 2 times a times b, which is minus a, is equal to 1. So you have a square equal to a negative number, right? So that means a cannot be a real number, right? I mean, if the square of a real number is never negative, okay? But we assume that a is a real number, so we're not considering this. So we're going to use a equal to b. Okay? So from the first equation, I get a equal to b, and I plug this into the second equation, okay? If you do that, we do it here. I'm sorry, I'm kind of being disorganized here, but I don't have any space to write here. So 2a times b, and b is equal to a, and that is equal to 1, right? So you have 2a squared equal to 1, so a is equal to plus minus 1 over square root of 2, and b is also plus minus 1 over square root of 2. Why? Because a is equal to b, right? So when a is 1 over square root of 2, b is 1 over square root of 2. When a is negative 1 over square root of 2, b is negative 1 over square root of 2. Okay? So what is I equal to, what is square root of I? We got two solutions for that, okay? One is, remember we had assumed it to be of a plus bi form. So you have two solutions for that, okay? When a is 1 over square root of 2, then you have this, 1 over square root of 2 plus 1 over square root of 2 times I. And when a is negative 1 over square root of 2, then you have this, okay? So you have two solutions for square root of I, okay? Isn't this cool? Like, you just needed to know the definition of I, and, you figured out what is square root of I, okay? All right? So now, what we're going to do is, we will go back to our first problem, the problem with which we started the session. We got the following result, which is minus infinity to plus infinity dx e to the power minus k1 x minus a squared minus k2 x minus b squared is equal to square root of pi k1 plus k2 e to the power minus k1 k2 divided by k1 plus k2 a minus b squared. Okay. So there's a note, okay, after the problem, which says what happens when k1 is minus ip1 and k2 is minus ip2. Okay, so you can see why I waited, right? I didn't talk about I, so now it's okay to talk about this problem when we have already discussed imaginary numbers. Okay, well, but there's really nothing much in this part of the problem, in the note, because all you have to do is to just replace k1 by minus ip1 and k2 by minus ip2. Okay, why am I talking about this? Because in Feynman's path integral, okay, these substitutions become important. Okay, so your expression, what you get is not what you see in Feynman's path integral is not this where k1 and k2 are real, but you see an expression in terms of imaginary numbers. Okay, so that's why I kind of I'm emphasizing this. Okay, so let's just substitute k1 and k2 by the following two expressions, and I'll get dx and then e to the power ip1 x minus a squared plus ip2 x minus b squared, right? I mean, if k2 is negative, the negative is positive, same as here. And on the right side, you have pi k1 plus k2, which is minus I times p1 plus p2, and then e to the power minus k1 times k2. Okay, so you have to be careful about the sign. So there's a negative sign, and then I times I is what? I square is minus. Remember, I square root of minus 1, so I square equal to minus 1. Okay, so there's a lot of negative signs here. Okay, so if you have done your math correctly, you should get this. Okay, you should get a positive sign I p1 p2 divided by p1 plus p2. Okay, And this part doesn't change, a minus b squared. Okay? And you can do this substitution in here, and you can check that you get this. Okay? All right. I think one of the things that I used here is, if you see 1 divided by I, okay, that is minus I. Okay? Why? Because I is minus I squared. Okay? So minus I, okay, so this is just minus I. Okay? So whenever you see 1, it means, it's negative of I squared. All right? So yeah, this is going to be important, algebraic manipulations like this. Okay, 1 over I is minus I. Okay? All right. So, okay, so you get this formula, okay? Now let's use this expression, okay, that we got. And I think we can do even better. So let's actually just use, okay, what I just showed you. So you have 1 divided by minus I, right? So that is going to be, you can write this as minus 1 divided by I, but minus 1 is I squared, right? So this is just I. So you can write this in a slightly more, normal looking form by bringing this I into the denominator. Okay, this times, the rest of the expressions, okay? E to the power I, P1, P2, divided by P1 plus P2, okay, A minus B whole squared. Okay, right, so let's use this result, okay, to do the second problem that I had assigned, in the previous session, okay, and that would be the last problem, in today's session, all right. So I've covered many things, so I'll let you just, go over them, okay. So this is the last problem, and in the next session we'll get back to where we had left, okay. It's like, I think it was we are discussing complex numbers, so we will mix the series expansion with complex numbers in the next session, okay. All right, so let's do the second assigned problem from the previous session, all right. And we'll be using this formula to do that. So let's write down this expression clearly, okay? And let's do the second problem. Okay, so let me just write down what we learned, okay, in the previous problem. So it's this integral really, okay, minus infinity to plus infinity dx e to the power I p1 x minus a squared plus p2 x minus b squared is equal to square root of I pi p1 plus p2 e to the power I p1 p2 divided by p1 plus p2 a minus b squared. Okay, so we're going to use this expression to prove, to integrate this expression, okay? This is a double integral, minus infinity to plus infinity, minus infinity to plus infinity, dx dy, e to the power I x minus a squared plus x minus y squared plus y minus b squared. Okay, you'll see this expression is also, it's going to be important in Feynman's path integral, okay? So you have a double integral. Okay, by the way, what is a double integral, okay? So, think of it as an iterated integral, okay? Like, when you integrate with respect to y, treat x as a constant, and then you integrate with respect to x, okay? So you do it in iteration, okay? First with respect to y, a single integral with respect to y, and then another single integral with respect to x, all right? And when you integrate with respect to y, you treat x as a constant, okay? So it's a very simple, straightforward extension of a single integral, all right? And the limits are from minus infinity to plus infinity, all right? And we're going to use this formula to do this integral, okay? So let's, and the solution is there in the, in appendix 7 of this book, okay? So let me just outline the proof of this, okay? You can find the complete solution, okay, in the book. So first what I'm going to do is that I'm going to integrate with respect to y, okay? So I'll write this as minus infinity plus infinity. This variable doesn't depend on y, right? So I'm going to write this first, and you have a dx, okay? And then minus infinity plus infinity dy, the rest of the expression. So you have e to the I x minus y squared plus y minus b squared, right? Okay? Now you see this expression, this integral is precisely in this form. By the way, x here is a dummy variable, okay? Which means that you can write you can replace x by u, for example. So you can write this as du u minus a u minus b. So this integral, in this integral, u is just y, okay? The integration variable is y, which is just u. Okay, so and you can compare. So if u is y, then your a is x and b is just b, okay? And p1 equal to p2 is equal to 1, okay? p1 is 1 and p2 is 1, right? So you can use this formula, okay, to evaluate this integral, and you will get something like square root of I pi divided by p1 plus p2, which is just 2, okay, times e to the power I, you have to calculate this, okay, for p1 equal to 1 and p2 equal to 1, and you will get half really, okay? And then a minus b should be x minus b squared. All right, so you see this is a function of x, right? So now, you have integrated out y, okay? You have this expression, but you still have to do the x integral, right? So let me just write down the x integral here. So you have minus infinity to plus infinity dx, and then you have e to the I x minus a squared, and then this expression, right? So which is this times e to the power I over 2 x minus b squared. All right, this is your, let me erase this part. Okay? Okay, so once again, you see this integral is of this form, right? I mean, if you just take the constant aside, so let's write the constant outside the integral, and inside the integral, you have minus infinity to plus infinity, okay? E to the I x minus a squared, I think you can write it in this form, plus, okay, half times x minus b squared, okay? So now you can see a is a, b is b, and the dummy variable is x, okay? So u is just x here, okay? So once again, you can use this formula, okay? But this time you have to use p1 equal to 1 and p2 is equal to half. All right? So, you'll have a constant term, okay? So this integral will give you a constant term times e to the power I over 3, this time it would be 1/3, times a minus b squared. Okay? So when p1 is 1 and p2 is half, then this fraction, okay, is just 1/3, okay, and you have a minus b, okay? So, and there's a constant which you can find out, okay, with proper values of p1 and p2, okay? All right, so you have basically done this double integral, okay? So let me write down the final expression, all right? So the final expression for this double integral is square root of I pi over 2 times square root of 2i pi over 3 times e to the power I over 3 times a minus b whole squared. Okay? And you can simplify this a little bit to get I pi over square root of 3 times e to the power I over 3 times a minus b squared. Okay? Now, this is a very important result, okay, in Feynman's path integral, all right? Notice some of the features of this, of this result, okay? One is that x and y are kind of an intermediate variables, okay? So you can think of this as a minus x squared, right, plus x minus y squared, plus y minus b squared. So do you see the symmetry? Like, a and b are two endpoints, right? So on one end you have A, and on the other end you have B, right? And these are like intermediate points, okay? So it's the square of the differences, okay, involving the intermediate points, okay? And you integrate out the intermediate points, and your answer depends only on the endpoints, okay? So as we will see later that, this relationship is, this property of the Gaussian integrals is one of the cornerstones, okay, of Feynman's path integral, okay? So what is that important feature? So what is, very, very briefly speaking, that important feature is if you integrate out the intermediate variables, you have the end result is another Gaussian, which depends, which has, a minus b squared in the argument of the complex exponential, okay? Like the square of the difference of the endpoints in the argument of the complex exponential, all right? Okay, so anyway, so this is this is what we set out to prove, okay? This is problem number 2, and you will see applications of that in, Feynman's path integral. With that, I, conclude today's session. So next time I will start with the discussion of complex numbers and series expansion mixed together, okay? Hope you enjoyed this video. Thank you for watching.